This is Chapter 21, Temperature, Heat, and Expansion. All matter, solid, liquid, and gas, is composed of continually jiggling atoms or molecules. Because of this random motion, the atoms and molecules of matter have kinetic energy. The average kinetic energy of these individual particles causes an effect we can sense, warmth. Whenever something becomes warmer, the kinetic energy of its atoms or molecules has increased. It's easy to increase the kinetic energy in matter. You can warm a penny by striking it with a hammer. The blow causes the molecules in the penny to jostle faster. If you put a flame to a liquid, the liquid also becomes warmer. Rapidly compress air in a tire pump and the air becomes warmer. When the atoms or molecules in matter move faster, the matter gets warmer. Its atoms or molecules have more kinetic energy. For brevity, which means briefness, in this chapter, rather than saying atoms and molecules, we'll simply say molecules, by which we mean either. So when you warm up by the fire on a cold winter night, you are increasing the molecular kinetic energy in your body. We're on page 307, Chapter 21, Temperature, Heat, and Expansion. Section 21.1, Temperature. The quantity that tells us how hot or cold something is compared with a standard is temperature. We express temperature by a number that corresponds to a degree mark on some chosen scale. Nearly all matter expands when its temperature increases and contracts when its temperature decreases. A common thermometer measures temperature by showing the expansion and contraction of a liquid, usually mercury or colored alcohol, in a glass tube using a scale. On the most widely used temperature scale, the international scale, the number 0 is assigned to the temperature at which water freezes, and the number 100 to the temperature at which water boils, at standard atmospheric pressure. The gap between freezing and boiling is divided into 100 equal parts, called degrees. This temperature scale is the Celsius scale. On the temperature scale used commonly in the United States, the number 32 designates the temperature at which water freezes, and the number 212 is assigned to the temperature at which water boils. This temperature scale is called the Fahrenheit scale. The Fahrenheit scale will become obsolete if and when the United States goes metric. The scale used in scientific research is the SI scale, the Kelvin scale. Its degrees are the same size as the Celsius degrees and are called kelvins. On the Kelvin scale, the number 0 is assigned to the lowest possible temperature, absolute 0. At absolute 0, a substance has no kinetic energy to give up. 0 on the Kelvin scale, or absolute 0, corresponds to negative 273 degrees Celsius on the Celsius scale. We will learn more about the Kelvin scale in Chapter 24. Earth formulas can be used for converting from one temperature scale to another and are often popular in classroom exams. Such arithmetic exercises are not really physics, so we will not be concerned with them here. Besides, a conversion from Celsius to Fahrenheit or vice versa can be very closely approximated simply by reading the corresponding temperature from the side-by-side scales in figure 21.1. The figure shows a thermometer. On the left side is Fahrenheit degrees. On the right side are Celsius degrees. Temperature and kinetic energy. Temperature is related to the random motions of the molecules in a substance. In the simplest case of an ideal gas, temperature is proportional to the average kinetic energy of molecular translational motion, that is, motion along a straight or curved path. In solids and liquids, where molecules are more constrained and have potential energy, temperature is more complicated. But it is still true that temperature is closely related to the average kinetic energy of translational motion of the molecules. So, the warmth you feel when you touch a hot surface is the kinetic energy transferred by molecules in the surface to molecules in your finger. Note that temperature is not a measure of the total kinetic energy of the molecules. There is twice as much kinetic energy in 2 liters of boiling water as there is in 1 liter. But the temperature of both liters of water are the same because the average kinetic energy in each is the same. Page 309, section 21.2, heat. If you touch a hot stove, energy will enter your hand from the stove because the stove is warmer than your hand. But if you touch ice, energy will pass out of your hand and into the colder ice. The direction of spontaneous energy transfer is always from a warmer substance to a cooler substance. The energy that transfers from one object to another because of a temperature difference between them is called heat. It is common, but incorrect with physics types, to think that matter contains heat. Matter contains energy in several forms, but it does not contain heat. Heat is energy in transit from a body of higher temperature to one of lower temperature. Once transferred, the energy ceases to be heat. In Chapter 8, we called the energy resulting from heat flow thermal energy to make clear its link to heat and temperature. In this and following chapters, we will use the term that scientists prefer, internal energy. When heat flows from one object or substance to another it is in contact with, the objects or substances are said to be in thermal contact. Given thermal contact, heat flows from the higher temperature substance into the lower temperature substance. However, heat will not necessarily flow from a substance with more total molecular kinetic energy to a substance with less total molecular kinetic energy. For example, there is more total molecular kinetic energy in a large bowl of warm water than there is in a small, red-hot thumbtack. Yet, if the tack is immersed in the water, heat does not flow from the water, which has more total kinetic energy, into the tack, which has less. It flows from the hot tack to the cooler water, from the thing at the higher temperature but less thermal energy, into the cooler thing that has more thermal energy. Heat flows according to a temperature difference, that is, average molecular kinetic energy differences. Heat never flows on its own from a cooler substance into a hotter substance. We will return to this concept in Chapter 24 when we look at thermodynamics. Page 310, Section 21.3, Thermal Equilibrium. After objects in thermal contact with each other reach the same temperature, no heat flows between them. We say the objects are in thermal equilibrium. To read a thermometer, we wait until it reaches thermal equilibrium with the substance being measured. When a thermometer is in contact with a substance, heat flows between them until they have the same temperature. We then know the temperature of the thermometer is also the temperature of the substance. So a thermometer, interestingly enough, shows only its own temperature. A thermometer should be small enough that it does not appreciably alter the temperature of a substance being measured. If you are measuring the temperature of room air, then the heat absorbed by the thermometer will not lower the air temperature noticeably. But if you are trying to measure the temperature of a drop of water, the temperature of the drop after thermal contact may be quite different from its initial temperature. Figure 21.4, somewhat like water in the pipes seeking a common level for which the pressures at equal elevations are the same, the thermometer and its immediate surroundings reach a common temperature at which the kinetic energy per particle is the same for both.